Hey everyone, welcome to this exciting new series on generative AI. In this video, we're starting right from the basics with an introduction to artificial intelligence and machine learning. Whether you're completely new to AI or looking to refresh your knowledge, I'll break down these concepts in a simple and easy to understand way. We'll cover what AI and machine learning are, how they work, and why they're becoming so important in today. So stick around, and by the end of this video you'll have a solid foundation to dive deeper into AI and its fascinating applications. 1. What is artificial intelligence AI? Artificial intelligence AI is the field of computer science that focuses on creating machines capable of simulating human intelligence. These machines are programmed to think, learn, and make decisions in ways that mimic human cognitive processes. AI systems can analyze vast amounts of data, identify patterns, and make predictions or decisions based on the data they receive. Over time, they can improve their performance through learning algorithms, becoming more accurate and efficient in solving complex problems. From voice assistants to autonomous vehicles, AI is transforming industries by enabling machines to handle tasks that typically require human intelligence. Key characteristics of AI. The key characteristics of AI include several essential abilities that allow machines to function intelligently. First is learning, where AI systems acquire information and develop rules to effectively use that information for future decision making. Next is reasoning, where these systems apply rules and logic to reach conclusions, whether they are approximate or definite. Another critical characteristic is self-correction, where AI continuously refines its performance by learning from past mistakes and improving over time. Finally, perception allows AI to interpret sensory input such as visual or auditory data to understand and make deductions about the world around it. Together, these characteristics enable AI to perform tasks that traditionally require human intelligence. Example. Example. An example of artificial intelligence AI in action can be seen in virtual assistants like Siri, Alexa, and Google Assistant. These AI powered systems are designed to recognize and process voice commands, allowing us to interact with technology using natural language. When a user asks a question or gives a command, the virtual assistant interprets the spoken language, searches for relevant information, and provides an appropriate response. Over time, these virtual assistants improve their accuracy and performance by learning from user interactions, adapting to individual preferences, and offering more personalized responses. This ability to learn and improve makes them smarter and more efficient with continued use. 2. What is machine learning ML? Machine learning ML is a crucial subset of artificial intelligence AI that emphasizes the development of algorithms enabling machines to learn from data. Unlike traditional programming where explicit instructions are provided, ML allows machines to learn and improve over time by identifying patterns in data. Through a process known as training, models are exposed to large datasets which help them make predictions, classify information, or make decisions based on the patterns they uncover. The more data these models are trained on, the better they become at making accurate predictions. This ability to learn autonomously without needing manual programming updates makes ML a powerful tool across various industries from healthcare to finance. How machine learning works. 1. Data collection. The first step in ML is gathering large amounts of relevant data from various sources. The quality and quantity of this data significantly impact the model's ability to learn effectively. Examples include images, text, transaction records, or sensor readings. 2. Data preparation. Once data is collected, it needs to be cleaned and formatted to remove noise, handle missing values, and ensure consistencies. This step may also include data transformation, such as normalizing values or converting categorical data into natal form so that the model can process the data efficiently. 3. Model selection. The next step is choosing the right algorithm model based on the task at hand. For example, decision trees, linear regression, or support vector machines might be used for tasks like classification, regression, or clustering, depending on whether the problem involves predicting categories or continuous values. 4. Training. The model is then trained by feeding it the prepared dataset. During this step, the model looks for patterns, trends, or relationships within the data by adjusting internal parameters, weights, and biases to fit the data. The goal is to minimize the error between the model's predictions and the actual outcomes. 5. Evaluation. After training, the model is evaluated by testing its performance on a separate set of unseen data called the validation or test dataset. This helps determine how well the model generalizes to new unseen data and reveals whether it is overfitting, memorizing the training data, or underfitting, failing to capture patterns. 6. Tuning. Based on the evaluation results, model tuning, hyperparameter optimization is done. This could involve adjusting the learning rate, the number of layers, or the complexity of the model to improve accuracy and reduce errors. This fine tuning ensures the model is better at making predictions. 7. Prediction. Finally, the trained and optimized model is deployed for use in real world scenarios. It can now process new data, make predictions, classify inputs, or provide insights based on the patterns it learned during training. Example. Example. An example of machine learning (ML) in action is spam email detection systems, which use ML algorithms to classify emails as either spam or legitimate. These systems are trained on large datasets that include various features such as email content, sender information, and user behavior. Initially, the system learns from patterns in the data like specific words, links, or sender domains that are commonly associated with spam. Over time, as users mark emails as spam or not, the system adjusts and improves its accuracy by incorporating this feedback into its learning process. This continuous learning enables the spam detection system to become more effective at identifying and filtering out unwanted emails, adapting to new types of spam content as they evolve. 3. Key types of machine learning. Machine learning (ML) is categorized into three main types. Supervised learning uses labeled data where the model learns from input-output pairs to make predictions like spam detection or price prediction. Unsupervised learning works with unlabeled data, aiming to find hidden patterns or clusters such as in clustering or market basket analysis. Lastly, reinforcement learning involves the model learning through interactions with its environment, receiving rewards or penalties to improve its actions over time, making it ideal for tasks like game playing or robotics. Each type serves specific purposes in training and applying machine learning models. A. Supervised learning. In supervised learning, models are trained using labeled data, meaning each input comes with a corresponding correct output. The model's goal is to learn the relationship between the inputs and outputs by analyzing these labeled examples. Over time, the model identifies patterns within the data that allow it to map new inputs to the correct outputs. Supervised learning is commonly used for tasks like classification, where the model predicts categories, e.g., spam Z, non spam emails, or regression, where it predicts continuous values, e.g., house prices. By learning from labeled data, supervised learning models can make accurate predictions on new unseen data. Applications. Supervised learning has a wide range of applications, particularly in classification and regression tasks. In classification, the model categorizes data into predefined labels such as detecting whether an email is spam or not. The model learns from labeled examples and uses this knowledge to classify new unseen emails. In regression, the model predicts continuous values based on input data. For example, in housing price prediction, the model is trained on historical housing data to predict the price of a house based on factors like location, size, and condition. These applications demonstrate how supervised learning models map inputs to outputs to make useful predictions. Example An example of supervised learning is training a model to recognize handwritten digits. In this case, the model is provided with a data set of images where each image of a digit 0 to 9 is labeled with the correct number. By analyzing the labeled images, the model learns to identify patterns such as shapes and shape pixel arrangements that correspond to each digit. Once trained, the model can accurately classify new unseen images of handwritten digits, making it useful for applications like automated digit recognition in postal services or bank check processing. B. Unsupervised learning. In unsupervised learning, the model is trained on data that is not labeled, meaning it doesn't have predefined outcomes or categories. The goal is for the model to discover hidden patterns, structures, or relationships within the data on its own. Unlike supervised learning, where the model knows what the output should be, unsupervised learning works by exploring the data to identify clusters, associations, or anomalies. This approach is useful for tasks like customer segmentation, where the model can group customers based on similar behaviors, or for anomaly detection, where unusual patterns in the data might indicate fraud or system errors. Applications Unsupervised learning has several key applications, including clustering and dimensionality reduction. In clustering, the model groups data points based on their similarities even without labeled examples. For instance, in customer segmentation, the model can automatically group customers with similar purchasing behaviors, helping businesses tailor marketing strategies for each segment. Another important application is dimensionality reduction, such as principal component analysis (PICA), which simplifies large datasets by reducing the number of variables while retaining the essential patterns. This is useful in fields like image processing or genetics, where high dimensional data can be difficult to interpret and manage. Unsupervised learning enables the discovery of meaningful patterns and structures in complex datasets. Example An example of unsupervised learning is grouping customers based on their purchasing behavior without prior knowledge of predefined customer segments. In this case, the model analyzes patterns in customer data such as purchase frequency, product types, and spending habits and groups similar customers together. The model does this without any labeled data or predefined categories. These groups or clusters can help businesses better understand customer behavior and tailor their marketing strategies or product recommendations for each segment. This approach is commonly used in retail and e-commerce to enhance customer experience and improve targeting efforts. C. Reinforcement learning. Way Reinforcement learning is a type of machine learning where agents learn to make decisions by interacting with their environment. The agent performs actions, receives feedback in the form of rewards or penalties, and adjusts its strategy to maximize the cumulative reward over time. Unlike supervised learning, where the correct outputs are provided, reinforcement learning allows the agent to explore different actions and learn from the consequences of its decisions. This approach is particularly useful for tasks where the environment is dynamic and uncertain, such as training autonomous robots, playing complex games like chess or Go, or managing self driving cars. Over time, the agent refines its strategy by learning which actions lead to the most favorable outcomes. Applications Reinforcement learning has several practical applications, particularly in fields like robotics, game AI, and autonomous vehicles. In robotics, reinforcement learning enables robots to learn tasks such as walking or grasping objects by receiving feedback from their environment and gradually improving their movements. In game AI, reinforcement learning is used to train agents that can make strategy decisions in complex games such as chess or video games by learning from trial error to develop winning strategies. In autonomous vehicles, reinforcement learning helps self-driving car make decisions about navigation, obstacle avoidance, and speed control by interacting with their environment and optimizing driving performance over time. These applications highlight the power of reinforcement learning in dynamic and complex environments. Example. An example of reinforcement learning is a self-driving car learning to navigate the road by staying in its lane and avoiding obstacles. The car interacts with its environment, receiving continuous feedback based on its actions. For instance, if the car successfully stays in its lane or avoids an obstacle, it receives a reward. If it veers off the lane or gets too close to another vehicle, it incurs a penalty. Over time, the car's driving system learns which actions lead to positive outcomes, adjusting its behavior to maximize safety and efficiency. This process allows the car to improve its driving performance and make smarter decisions on the road. 4. The relationship between AI and machine learning. Uh, the relationship between artificial intelligence, AI, and machine learning, ML, is that AI is the broader field that encompasses the idea of machines being able to perform tasks intelligently, mimicking human cognitive functions such as problem solving, decision making, and learning. Machine learning is a specific subset of AI that focuses on enabling machines to learn from data and improve over time without being explicitly programmed for each task. While all machine learning techniques fall under the AI umbrella, not all AI approaches rely on machine learning. Some AI systems may be rule based or rely on hard coded logic without any learning involved. Therefore, while ML is an essential part of AI as a whole includes various other methods for creating intelligent systems. Hierarchy visualization. The hierarchy of artificial intelligence and AI can be visualized as a broad field with several subfields and techniques. At the top is AI, which encompasses all forms of machine intelligence. A significant branch of AI is machine learning (ML), which focuses on teaching machines to learn from data. Within ML, there are three main types: supervised learning, where models learn from labeled data; unsupervised, where models discover hidden patterns in unlabeled data; and reinforcement learning, where agents learn through interaction with their environment using rewards and penalties. In addition to machine learning, there are other AI techniques such as rule based systems and expert systems, which rely on predefined rules and logic rather than learning from data. This hierarchy illustrates the relationship in various AI techniques with machine learning be a key component but not the only method of our 5. The role of data in machine learning. Data plays a crucial role in machine learning (ML) as it serves as the foundation on which models are built and trained. The performance and accuracy of an ML model are directly influenced by both the quality and quantity of the data. High quality data that's clean, well labeled, and relevant allows the model to learn meaningful patterns and machiavelli. On the other hand, if the data is noisy, incomplete, or biased, the model's performance will suffer. Similarly, a larger quantity of diverse data enables the model to generalize better and perform well on new unseen data. Without sufficient or good quality data, even the most advanced algorithms will struggle to produce reliable results. Thus, data is the cornerstone of machine learning, and the success of an AI project depends heavily on how well the data is collected, prepared, and managed. Importance of data. 1. Training. The model learns by identifying patterns, relationships, and trends from the training data. High quality training data allows the model to learn accurately and build a strong foundation for making predictions. 2. Validation. A separate dataset, known as the validation set, is used to fine tune the model's parameters. It helps prevent overfitting by ensuring that the model generalizes well beyond the training data. 3. Testing. After training and validation, the model is tested on unseen data, the test set. This step evaluates the model's ability to generalize and perform well on real world data, ensuring it can handle new inputs effectively. Data challenges J. 1. Quality. Poor quality data, such as data with missing values, errors, or inconsistencies, can lead to poor model performance. If data is not accurate or relevant, the model may learn incorrect patterns, leading to unreliable predictions. 2. Data preparation. Cleaning and processing data are essential steps that often take a lot of time and effort. This process includes removing duplicates, handling missing values, normalizing data, and transforming variables into a format suitable for the model, all of which are crucial for improving the model's accuracy. 3. Privacy. When working with sensitive or personal data such as healthcare or financial information, adhering to privacy regulations like GDPR is critical. Ensuring that data is handled securely and ethically while maintaining kindness with legal requirements can be a significant challenge. Example. An example of the importance of data in machine learning is Netflix's recommendation system, which relies heavily on vast amounts of user data. The system collects information such as users' viewing history, ratings, and even interactions with content, e.g., likes, dislikes, and watch duration. By analyzing this data, Netflix's machine learning algorithms identify patterns in user preferences and viewing habits. These insights allow the platform to suggest personalized content such as TV shows and movies that are likely to appeal to individual users. As more data is collected, the recommendation system continuously improves, becoming more accurate in predicting what content will keep users engaged. This example highlights how critical high quality data is to delivering personalized data driven services like Netflix's recommendations. 6. Common applications of AI and machine learning in healthcare. Diagnosis assistance AI systems are increasingly used to analyze medical images such as X rays, MRIs, and CT scans to detect diseases more accurately and efficiently. By recognizing patterns in medical imaging data, AI can assist doctors in making faster and more accurate diagnoses. Predictive analytics AI models are employed to predict patient outcomes, identify potential risks, and even forecast disease outbreaks. By analyzing historical patient data and real time health information, I can provide early warnings for medical conditions or help manage public health crises like disease outbreaks. Personalized medicine AI helps tailor treatments based on individual patient information, including genetic data. This allows for more precise and effective treatment means offering a more personalized approach to healthcare and improving patient outcomes. Example, IBM Watson Health uses AI to assist oncologists in creating personalized cancer treatment plans. By analyzing vast amounts of medical literature and patient data, Watson helped doctors identify the best possible treatments tailored to each patient's genetic profile and medical history. B. Finance. Fraud detection. AI systems are used to detect fraudulent transactions in real time by analyzing patterns in transaction data. Machine learning models are trained to identify unusual or suspicious activity, helping financial institutions prevent fraud before it occurs. Risk assessment. Machine learning algorithms assess credit risk by analyzing a borrower's financial history, income, and other factors. This allows banks and lending institutions to make more informed and accurate decisions when approving loans, minimizing the risk of defaults. Algorithmic trading. AI models are used in algorithmic trading to make trading decisions based on predictive models. These algorithms analyze market data and execute trades at high speed, maximizing profits by predicting market movements. Example, many banks use machine learning algorithms to monitor transactions and detect anomalies. These algorithms flag suspicious activity such as unusually large withdrawals or transactions from unfamiliar locations, enabling banks to respond to potential fraud quickly and protect customers. C. Retail and e-commerce. Recommendation engines, AI powered recommendation engines analyze customers' browsing history, past purchase, and preferences to suggest relevant products. This personalized approach enhances the shopping experience by presenting items that align with individual tastes and needs, driving customer engagement and sales. Inventory management, machine learning, and algorithms are used to predict stock requirements by analyzing historical sales data, seasonal trends, and customer demand. This enables businesses to optimize their supply chain, reduce excess inventory, and avoid stock shortages, ensuring efficient operations. Customer service AI powered chatbots are commonly used to handle customer inquiries, provide support, and even assist with transactions. These virtual assistants are available 24/7, improving response times and reducing the workload for human agents, which enhances customer satisfaction. Example, Amazon's recommendation engine is a prime example of AI in retail. By analyzing users' browsing behavior, purchase history, and even product viewed by similar customers, Amazon personalizes the shopping experience for each user, offering tailored product suggestions that increase engagement and drive more sales. D. Transportation and logistics. Autonomous vehicles, self-driving cars, and trucks rely on AI to navigate roads, recognize obstacles, and make real-time decisions. By processing data from sensors and cameras, AI enables these vehicles to drive safely without human intervention, reducing accidents and improving transportation efficiency. Route optimization: AI helps logistics companies and delivery services determine the most efficient routes for drivers. By analyzing factors like traffic conditions, weather, and delivery locations, AI ensures that deliveries are completed and more cost effectively, improving overall operational efficiency. Predictive maintenance: machine learning models are used to predict when vehicles or equipment will require maintenance by analyzing historical performance data. This helps transportation companies anticipate failures before they occur, reducing downtime and maintenance costs. Example uses machine learning for surge pricing and route optimization during high demand periods. Uber's algorithms adjust prices in real time, ensuring that riders are matched with available drivers more efficiently. Additionally, Uber's ML powered system optimizes routes for drivers, reducing wait times and improving the overall experience for both riders and drivers. E. Natural language processing (NLP). Language translation: AI powered systems are used to translate text or speech from one language to another in real time. These systems utilize machine learning models to provide accurate and context aware translations, making communication easier across language barriers. Sentiment analysis: machine learning algorithms analyze text data to determine the sentiment behind it, whether it's positive, negative, or neutral. This is particularly useful for businesses monitoring customer feedback, product reviews, or social media posts to gauge publish outcome. Voice recognition: AI systems convert spoken language into written text through voice recognition technologies. These systems are trained on vast datasets of speech patterns, enabling them to transcribe spoken words with high accuracy, which is useful in virtual assistants and transcriptions. Example, Google Translate uses deep learning models to improve the accuracy of its translations. By analyzing millions of text examples, it learns the nuances of language, allowing it to provide more accurate and contextually appropriate translations across various languages, making global communication more seamless. F. Manufacturing. Quality control AI systems often using computer vision inspect products on production lines for defects. These systems can detect even the smallest inconsistencies or flaws in products, ensuring higher accuracy and faster quality checks compared to manual inspections. Robotics AI powered robots are increasingly used in manufacturing to perform complex tasks such as assembly, welding, and packaging. These robots can work faster and more precisely than humans, improving efficiency and reducing errors in production lines. Supply chain optimization AI helps manufacturers predict demand, manage inventory, and streamline supply chain operation. By analyzing historical data, market trends, and current conditions, AI enables manufacturers to reduce excess inventory, avoid stockouts, and optimize the flow of goods. Example: AI is used to monitor production lines in real time, helping manufacturers detect issues early, reduce downtime, and improve overall efficiency. This real time monitoring allows for proactive adjustments, ensuring smooth operations and maintaining high production quality. 7. The future of AI and machine learning. Ah, Advancements in AI. Artificial General Intelligence AGI, a significant future goal in AI is the development of artificial general intelligence. Unlike current AI, which is specialized for specific tasks, AGI would have the ability to understand, learn, and apply knowledge across various domains, much like human intelligence. This would enable machines to think and reason in a general, flexible way, potentially transforming industries and everyday life. Explainable AI (XI). As AI systems become more integral to decision making, the need for explainable AI is growing. SAI refers to AI models that provide transparency and insights into how decisions are made. This will make AI systems more understandable and trustworthy, especially in fields like healthcare, finance, where understanding the reasoning behind AI decisions is critical for ethical and legal compliance. Edge AI, the future of AI will see a rise in Edge AI, where AI algorithms run directly on local devices such as smartphones, cameras, or IoT devices rather than in centralized cloud systems. This reduces latency, enhances real time decision making, and improves privacy as sensitive data remains on the device rather than being transmitted to external servers. B. Generative AI. Content creation. Generative AI is increasingly used to create realistic content such as images, music, and text. These AI models learn from vast datasets and can generate creative outputs that closely resemble human made content, revolutionizing fields like design, writing, and entertainment. Deepfakes. One of the controversial applications of generative AI is the creation of deepfakes, which are synthetic media that alter or imitate someone's likeness. This technology can be used to convincingly replace faces in videos or manipulate audio, raising concerns about misuse and ethical implications. Example: OpenAI's Gem 3 is a leading example of generative AI. It generates human like text that can be used for a variety of purposes, including writing articles, answering questions, automating customer support, and even generating code. GP3's ability to create coherent and contextually appropriate text showcases the potential of generative AI in numerous applications. C. Ethical considerations. Bias and fairness. One of the major ethical concerns in AI is addressing bias and fairness. AI systems trained on biased datasets can unintentionally perpetuate societal biases, leading to unfair outcomes in areas such as hiring, lending, or law enforcement. Ensuring fairness in AI development is crucial to prevent discrimination and promote equity. Privacy. With AI systems relying heavily on vast amounts of personal data, privacy is a key concern. Protecting individual data while using AI for decision making is critical, especially in sensitive areas like healthcare and finance. Safeguarding user data and ensuring it is not misused or exploited is an ongoing challenge in AI. Regulation. As AI becomes more powerful and widespread, regulation is essential to ensure responsible development and deployment. Governments and organizations are working to establish policies that govern AI's growth, ensuring that its use is ethical, transparent, and beneficial to society while minimizing potential harms like misuse, bias, and privacy violations. The social impact. Employment. AI has the potential to displace certain jobs by automating repetitive and manual tasks. However, it will also create new opportunities in fields related to AI development, management, and oversight. As industries adopt AI, there will be a growing demand for professionals with AI expertise, shifting the job market toward more specialized tech-focused roles. Education. AI is set to revolutionize education by providing personalized learning experiences, automating administrative tasks, and offering new ways to engage students. However, this shift will require AI literacy to be incorporated into education systems, ensuring future generations are equipped to understand, interact with develop AI technologies. Healthcare. AI is already transforming healthcare by improving diagnostics, treatment plans, and patient care through data driven insights. While these advancements offer immense benefits, they also raise important concerns about data privacy and patient consent. The ethical management of sensitive medical data and ensuring patient autonomy in decision making are critical issues as AI becomes more integrated into healthcare systems. And that wraps up our introduction to AI and machine learning. I hope you now have a clearer understanding of what these terms mean and how they fit into the world of technology. In the upcoming videos, we'll dive deeper into how AI systems are built, explore different algorithms, and look at real world applications of AI. If you found this helpful, make sure to hit the like button and subscribe for more AI tutorials. Thanks for watching, and I'll see you in the next video.